So if you have any question, don't forget that if it's important question, you can ask them now. If not, it's better to wait for the end of the lecture. Go on, Marc.
Okay, thanks, Christophe, and thanks everyone for joining again. Welcome back for the second week. I'm happy to be opening the week again. So I apologize in advance. I hope I will not be too fast and go through too many things, but I mean, we have to finish this lecture in 1 hour, and then there will be related lectures also by Andrew Strominger in 1 hour. And then later this week, lectures which I will mention will refer a bit to, I think, what we learn here. So hopefully this will be the continuity. So I hope you don't mind if I rush a bit today because of this. So just to summarize, what we did last Tuesday was to discuss a bit the asymptotic structure of three-dimensional gravity. And this is because it's a bit easier than four-dimensional gravity, which I will briefly mention at the end, hopefully today. So just to briefly summarize what we did at the end of the previous lecture. So we used these so-called null Bondi coordinates, which led to this form of the space-time diagram, to discuss on-shell metrics and asymptotic symmetries in three-dimensional gravity. So we mentioned these solutions, so I go through this a bit quickly, in so-called Bondi Gauge. So what is important on this slide, as we explained already, is this line element written in the middle. And so this line element, as we see, depends on two functions of retarded time u and the angular coordinate phi. And these coordinates are the 3D analog of the so-called Bondi mass aspect and the angular momentum aspect. So we said that these are exact solutions to three-dimensional gravity. So a family of solutions parameterized by these two free functions. Then we looked at the residual symmetries. We defined these as the symmetries generated by vector fields, which preserve our family of metrics in the sense of the first equality given here. Then we derived the transformation behavior of the fields of the on-shell metrics M and N under these diffeomorphisms. We said that F and G were actually, with a slight abuse of language, but this will be more explicit later. These are called super translations and super rotations. I also mentioned this modified bracket, which is a slight modification of the Lie bracket that you can compute. And this modification is due to the fact that, as you can see here, in the R component of this asymptotic killing vector, there is a dependency on the fields of the theory themselves, because there is an N function in the radial component of this vector. So this vector field is field dependent. And for this reason, if you want to compute the bracket of these vector fields, you have to modify it and define this star bracket instead of the usual Lie bracket. We briefly mentioned the geometrical meaning of these enhanced Poincaré transformations and said that these were actually arbitrary angle dependent translations and Lorentz transformations. And this was the illustration here of the super translations. And then we computed the charges. There was a subtlety on this slide, which I skipped, and I will still skip it today because it's not important for the rest of the lecture. So I will just skip this, but the important thing is that we're able to show explicitly that these charges are explicitly conserved. And then we computed what is interesting to us, namely the asymptotic symmetry algebra. This is the algebra which we obtained. And then we said that in the flat limit, this is something which maybe we recognize, or at least we have heard because of all the recent work in the literature. This is called the Bms algebra. And this is the three-dimensional, so BMS3 algebra. Then what I didn't mention, or very briefly at the end of the previous lecture, is that if we do not take the flat limit, if we still work with the cosmological constant, in the case where we are in ADS, so where the cosmological constant is negative, then we can do this slight redefinition of the diffeomorphism generators. And if we do this, we put the asymptotic symmetry algebra in the famous form of the double Virasoro algebra. So this was the original result of Brown and Hainaut, which was in fact kind of the starting point, the seminal work behind holography and ADS3 CFT2. And again, we mentioned that this is an infinite dimensional extension of SO22, which is the isometry algebra of ADS space. Okay, I will skip this. So now to start with something new now, I want to mention, and to end with three-dimensional gravity, I want to briefly mention the Chern-Simons formulation, because this is something which is important to know, and that you will see in many papers on three-dimensional gravity and many lectures. So the Chern-Simons formulation is essentially yet another way to rewrite three-dimensional gravity. So we have already seen two ways. So the first way is, of course, using the metric formulation and the familiar Einstein-Hilbert Lagrangian. What we actually used in this section was not the metric formulation, but rather the first order formulation. So using a triad and a gauge connection. And in fact, this third formulation, so-called the Chern-Simons formulation, is something which pushes even further, in a sense, the first order formulation in terms of a connection and a triad. Because what we will do in the Chern-Simons formulation is actually combine the triad EI. So I remind you that I are internal Lie algebra indices. So we will combine now the triad E and the connection omega into a connection capital A, which, so we can see with this definition that we have one new field, the connection, but this field A, our new gauge connection now, is built with 6 generators, because we have the 3 generators Ji, which are the generators of the Lorentz transformations in the formulation in terms of a connection and a triad. And we have the 3 components, the 3 generators Ti. So remember that in the flat case, we showed that J and T form the Poincaré algebra. And in the ADS case, J and T form the SO22 algebra. So using these 6 generators, we can define a new gauge connection, which is just a combination of the connection omega and the triad E. Now, just using this definition, this is the only piece of information that we need to show this equality. So I let you show this as an exercise. This is just a proof that if we take what we call the Chern-Simons Lagrangian, so this is the 3 form which is written here. So A wedge dA plus 1/3 commutator of A wedge A. This is the so-called Chern-Simons Lagrangian. If we use the definition of A in terms of omega and E, we can show that the Chern-Simons Lagrangian explicitly reduces to this sum of 4, 5, 6 of 8 terms. So now you see that in these 8 terms, there is something which I left completely implicit, namely this bracket here, this angled bracket between the generators. So here it's between J and J, between J and T, between T and T. And I also left implicit this Lie algebra bracket. So this squared bracket here. So this is something we have to specify. We have to specify because this is part of the data that specifies the gauge group of the theory, of the Chern-Simons theory that we are considering. So for example, as an illustration here, we can take, so we have to specify to give a meaning to this Chern-Simons Lagrangian and to see what it actually is. We have to specify the meaning of this bracket and of this pairing between the generators. So for the bracket, we can simply take the bracket which we already derived earlier, which is the bracket again of the algebra of isometries. So this is the commutation relations between the generators T and J. Again, in the flat case, for example, you see that this is just the 2 + 1 dimensional Poincaré algebra. And then this pairing, well, for example, you can choose a pairing in the case of these generators J and T, which pairs together the generators J and T, and it pairs them by giving there's just a factor of 1/2 for convenience and the internal metric eta ij, and the other 2 pairings are vanishing. Now, if you use this piece of information, so the brackets and the pairings, we can show, and I again invite you to show this explicitly, that the above expression for the Chern-Simons Lagrangian reduces to, well, just the Einstein-Cartan Lagrangian plus a boundary term. So in fact, we have just shown here that we can equivalently rewrite the Einstein-Cartan Lagrangian. So the first order Lagrangian in terms of a connection and a triad, we can equivalently rewrite it up to a boundary term as a transamince theory, as a transamince Lagrangian for a gauge connection A. The only information which we have to specify when we do this is which generators, J and T, we use to define the connection A. So which brackets and also which pairings we use to pair these generators together. Just as a remark here, because sometimes this is a source of confusion in the literature, I just want to point out that equivalently, we could have made just a slightly different choice. We could have, in fact, considered, so here above, we have considered one connection with 6 generators, 3 generators J and 3 generators T. But I want you to convince yourself that it's completely equivalent to actually use 2 connections, A plus minus, which are defined in this way, with only 3 generators J. And if you do this, you can just equivalently write the Einstein-Cartan Lagrangian. But now instead of being a single transamince Lagrangian, you will have to take the difference between 2 transamince Lagrangians. And I just want to mention this because sometimes in the literature, you see the statement that gravity in 3 dimensions is equivalent to 2 copies of transamince theory. And this is a bit, said like this, it's a bit slightly misleading because it actually depends on how you construct your transamince connection and how you choose to represent the gauge algebra.
Marc?
Yes?
I think some people are unclear about what the pairing are and the definition of what a pairing is and the notation. Yeah, so the pairing is just a bilinear form on the algebra of J and T. And so you notice that, in fact, maybe if the question is whether I could have chosen also a non-vanishing pairing for between J and T and T, well, the answer is yes, but again, so I didn't show it here. If you were to choose a non-vanishing pairing between the generators J and T, well, in this case, you would not, the transamince Lagrangian would not reduce to the Einstein-Cartan Lagrangian. You would have another Lagrangian, which actually gives equivalent equations of motion, but it's another inequivalent Lagrangian, but it has the same equations of motion. So this pairing, I didn't want to call it the trace because here it's not, strictly speaking, a trace, because you see that if I was tracing the product of 2, for example, SL2R generators, I would not get 0. So this is why I just call this a pairing and not a trace. So it's just, if you want at this stage, a notation that tells us that whenever we have J and T, this gives us eta at J, and J with J is 0, T with T is 0. So now the point is that with this transamince theory, you can basically using all the ingredients that we introduced earlier. So again, as an exercise, I invite you to check that we have all the material, all the tools at this point to completely define the covariant phase space for this transamince theory. So we can compute, of course, the equations of motion. So the equation of motion of this transamince Lagrangian is just that the curvature of A is equal to 0. We can compute the symplectic potential. And again, we should know now a bit how to read and guess what the symplectic potential will be, because we look at the transamince Lagrangian and we see that the only place where a derivative appears is here. So we have the term A wedge dA. So when we take the variation and integrate by parts, it's kind of clear that the symplectic potential that we will get is theta equals delta A wedge A. Now from this, we can well use the covariant phase space formalism that we introduced and compute the charges associated to gauge transformations of the connection A. For the charges, we'll find these surface integrals. So a charge with gauge parameter alpha is given by the integral of alpha times A. Again, the algebra between these charges reproduces the algebra of the isometries that we started with. So the algebra of J and T. So this is this bracket here up to a central extension. So just like it was the case, this is essentially the same bracket that we derived in the first order formulation in terms of a connection and a gauge field. But now instead of having 3 separate brackets for the generators that we called J and T earlier, now we have a single bracket for the charge for the generator F. And again, this is just because in the transamince formulation, we have repackaged the Lorentz transformations and the translations, so J and T, into a single object and into a single connection, which is capital A.
And again, you can show in Chern-Simons theory that you can again realize the diffeomorphisms as field-dependent gauge transformations. So for a diffeomorphism, this is just realized as a charge of a Chern-Simons gauge transformation, where the gauge parameter is now a vector field contracted with the gauge connection. So the reason why I mentioned this is that Chern-Simons theory is typically the starting point that people use. So it's the most convenient way to derive the boundary dynamics of three-dimensional gravity. We already mentioned very briefly, and we didn't go into details, that some of these algebraic structures that we discovered by looking at the charge algebra of three-dimensional gravity. So these charges, they are surface charges, they live on the boundary. Some of these structures, they are actually, well, they are what they are because secretly on the boundary of three-dimensional gravity, there is a boundary theory, which is a conformal field theory. And the way to show this, to extract the boundary dynamics of three-dimensional gravity, is typically to use the Chern-Simons formulation. So what happens in three-dimensional gravity, you can think of it in the following way, is that, well, since this is a topological theory, there are no degrees of freedom in the bulk of three-dimensional gravity. So the only non-trivial information, the only non-trivial things are essentially encoded on the boundaries. And this is what we showed, in fact, explicitly the form of the charges living on the boundary, also the form of the charge algebra. And it turns out that because the theory is topological, there is essentially a way of writing the theory on shell and of making the bulk of the theory completely disappear and reducing it to a boundary theory. So I will make this explicit in a minute on a simpler example. But essentially, what we should just keep in mind, if you're interested, you can, for example, look at this literature. Essentially, this procedure of extracting the boundary dynamics of three-dimensional gravity is essentially a way of producing lower dimensional boundary field theories, so namely two-dimensional boundary field theories, which have a symmetry which actually reflects the symmetry that we have discovered by looking at the charge algebra of three-dimensional gravity. So in the ADS case, we showed that the asymptotic symmetry algebra was a double Virasoro algebra, a pair of commuting Virasoro algebras. And in the flat case, it was this example of this BMS3 algebra. So there is essentially a way presented in these two references, for example, to write down Virasoro or double Virasoro or BMS invariant 2D boundary field theory. And this is most easily done by using the Chern-Simons formulation. So the one way to understand this, instead of doing the complicated calculation in the real 3D gravitational case, we can study as a toy model abelian Chern-Simons theory. And this is of physical importance because typically this has applications in condensed matter physics. So it's also maybe useful to mention this. So to do this, we can do it explicitly on one slide. We can look at the Lagrangian of abelian Chern-Simons theory. So for this, you notice that this is the same Lagrangian that I gave on the previous slide, except that now it's abelian. So this commutator here is not present. So we just have A wedge dA. It's a very simple Lagrangian. Again, I invite you to check that the charge algebra for this abelian Chern-Simons theory is a centrally extended U1 charge algebra. So if I take A to be, for example, a U1 gauge field, the gauge transformations are U1 gauge transformations generated by the boundary charge F, and the bracket between F smeared with alpha and F smeared with beta is a U1 current algebra with a central extension alpha d beta. Now to kind of explain where this can happen, I just want to point out that if you study a scalar field on a circular boundary, so imagine that you have a circular boundary parametrized by an angle phi. If we study a scalar field on this circular boundary with this canonical Poisson bracket between phi and phi dot, if I just denote this plus minus derivative by this chiral combination of t and phi, now we can check explicitly that the Poisson bracket between the chiral currents d plus phi or d minus phi is actually equal to this centrally extended bracket of the charge algebra of abelian Chern-Simons theory. So this is to show that this U1 current algebra with central extension of abelian Chern-Simons theory, there is a place where it also appears. It's when we look at the algebra of these chiral currents of a scalar field on the boundary. We get the same central extension, alpha 1 d alpha 2. I also invite you to check this as an exercise. Well, the reason for this is that we can actually show that explicitly now by looking at the boundary dynamics, that on the boundary of this abelian Chern-Simons theory, if we define this on a solid cylinder, we can show explicitly that this reduces to the action for a chiral scalar field. So to show this explicitly, first we can put the Chern-Simons action in a Hamiltonian form. So the first thing to do is to explicitly pick coordinates here. So the coordinates I have chosen to be t, r, and phi, the angular coordinate. So we can think of the spacetime M as being a solid cylinder. Now here I have just written the action in Hamiltonian form. And to do this, I have produced a boundary term. And this boundary term is just the integral of the component AT and the component A phi. And you see that this is indeed the action in Hamiltonian form, because here you have the canonical term with the time derivative. So these first two terms are essentially telling us that on a spatial slice of this solid cylinder, we have the phi and the r components of the gauge field, which are canonical variables. And then we see that the time component of the Chern-Simons gauge field is a Lagrange multiplier, which enforces a constraint, namely that the spatial component of the curvature is vanishing. Now, because of this, we can see that if we actually integrate over the time component, the Lagrange multiplier, so imagine that we're computing, for example, the path integral of this theory, and we path integrate over the Lagrange multiplier AT. This is going to enforce the constraint that the spatial component r phi of the curvature is vanishing. So this constraint is actually solved. It's telling us that the r and phi components of the gauge field are pure gauge. So if the component f r phi of the curvature is vanishing, this essentially tells us that the r phi components of the gauge field are of the form dr phi of alpha. So now if we explicitly plug this in the Hamiltonian form of the action which we had just above, so we explicitly plug the fact that AR phi are pure gauge, well, we can show explicitly that the bulk term reduces identically to only a boundary term. So you see that on the boundary, this minus AT A phi, which is here, has become this minus AT D phi alpha, because A phi is a flat gauge field, so it's of the form D phi alpha. And the bulk here above has produced this boundary term here, dt alpha d phi alpha. So now what is important is to actually notice that, or to discuss what we should do with this time component, which is on the boundary now. You notice that if we are a bit too naive, and if we say that we impose all of the equations of motion of Chern-Simons theory, so all the equations of motion, they would tell us that the time component is also flat, right? So if we're maybe tempted to say that AT is also dt of alpha, but you see that if we take the time component to be also pure gauge, to be of the form dt of alpha, this would reduce to 0. And we don't want this, and luckily for us, this is inconsistent. We cannot impose this to be flat, because this is not compatible with the boundary conditions of the theory. So to see this, we have to look at the symplectic potential, and look at, so for the boundary conditions, we have to look at the symplectic potentials, evaluated on the boundary of this solid cylinder. So the boundary is parameterized by t and phi. So we look at the t phi components of the symplectic potential. And so we see that to have a good variational principle, the most general boundary condition, which we can impose here, is to say that the t and phi components of the gauge field are actually proportional. So I use this proportionality, I denote it by just a velocity, v. So I say that at, the time component, is equal to v times the angular component a phi. So if now we plug this into this on-shell action that we have, well, we get exactly two-dimensional action living on the boundary of the manifold. And this is precisely the action for a chiral scalar field. So by chiral, I mean that if you look at the equations of motion here, you would find that this is a scalar field which has only left or right movers, depending on how you choose the velocity v. So this is just a simple illustration on abelian Chern-Simons theory that looking at the charge algebra, we find the U1 current algebra with a central extension. There was a small argument to say that this is maybe physically coming from a boundary theory, which is a scalar field, but with only left movers or right movers, so a chiral scalar field. And we showed explicitly by reducing Chern-Simons theory on shell, imposing part of the equations of motion, solving the constraints, we obtained explicitly the two-dimensional action for a chiral scalar field. So this is just a very simple toy example of what one can do in the non-abelian case. And in the non-abelian case, of course, this, as we just argued on the slide before, this non-abelian Chern-Simons theory will actually describe 3D gravity. And doing this procedure, we can actually produce two-dimensional boundary theories whose symmetries are exactly the symmetries of the charge algebra of three-dimensional gravity. So namely, for example, a double Virasoro algebra or a BMS3 algebra. Okay, so this ends this section on 3D gravity. So I give some references here. So this reference by Carlip is just some generalities on 3D gravity and also the link with conformal field theory, which unfortunately we could not cover. Also the relationship with the BTZ black hole, which we described a bit. Then for more details on the three-dimensional BMS group and algebra, I refer you to the thesis of Oblak. And then there is this review by Donnet on the asymptotic dynamics of 3D gravity. So in principle, hopefully with the material that we covered, you should be able to go and look at these references and in principle, understand at least why we're doing, why people are interested in these things and what is going on. And then hopefully work out all the technical details. Okay, so now that we covered 3D gravity, I just want to briefly end and mention the application to four-dimensional gravity. So of course, this is a much more complicated topic, and this is also still something which is heavily studied today, so something which is still going on. And hopefully so there are 3 other lectures this week, and hopefully these 3 lectures will give you maybe a more detailed idea of how this can be used and applied in four-dimensional classical and quantum gravity. So I just want to present you a bit some preliminary material, and then hopefully the rest of the lectures will tell you more. Okay, so the idea in four-dimensional gravity, again, this was our motivation when we introduced in the first place this notion of asymptotic symmetries in three-dimensional gravity. The idea is that we want to study gravitational radiation far away from sources. So of course, the story of the study of gravitational waves is very long and intricate, and there's contribution by many people. But here I just want to mention a few papers, namely these very influential papers by Bondi, van der Burg, Metzner, and Sachs. So between the 60s and then 62. I will a bit present the framework which was developed in this series of papers. Actually, at the same time, Newman and Penrose were also working on the understanding of gravitational radiation far away from sources. And in a paper in 62, they introduced what is now known as the Newman-Penrose formalism using null tetrads. And then a year later, Penrose introduced his famous conformal compactification in this paper, Asymptotic Properties of Fields and Spacetimes. So essentially the idea, so I just quote these just a very few references because this is what I want to mention in the rest of the talk. The idea here is, again, we take the diagram which we had earlier, except that earlier we were in three-dimensional gravity, so there could not be any object in the middle here because there was no, again, as we said, the theory in 3D is topological. There are no gravitational waves. Even if there are black holes don't emit gravitational waves. So now we are in 4 dimensions. We can imagine that there is some complicated physics going on here. For example, a black hole with an accretion disk or doing something complicated and emitting gravitational radiation. And then eventually we want this to be observed by someone. So I just want to contrast very briefly the two formalisms so that you know that these two formalisms exist and that you know that at least they are related. And I will only give a few details on one of the formalisms, namely the Bondi formalism. So I skip very quickly over the Penrose formalism. I invite you to read this maybe later. But so what I just want to mention here is that maybe I flash all the slides. So as I showed on the previous slide, these developments by Bondi and Sachs and collaborators were happening at the same time as the work of Penrose and Newman. In fact, Penrose gave a much more, in a sense, covariant and geometrical description of asymptotically flat spacetimes. But you see, if you read a bit these definitions of asymptotically flat spacetimes, which I give here, it can seem maybe a bit abstract and a bit maybe too geometrical in a sense. So either we really get used to this more abstract and geometrical formulation, or we can actually be a bit more hands-on and try to generalize what we did in 3-dimensional gravity. And this we can do using the so-called Bondi-Sachs formalism. So this is already what we used in 3D, the 3D Bondi-Sachs formalism. Now we can just generalize this to 4D, and I just want to spend a few minutes highlighting the differences between 3D and 4D, yes, so we should have enough time to do this. So you will see that the Bondi formalism is a bit more hands-on in a sense. It uses an explicit coordinate system and explicit fall-off condition for the fields. And in this formalism, it's a bit easier, a bit more immediate, I think, at least. It's a personal opinion also. It's a bit more immediate to identify the asymptotic symmetries and the group of asymptotic symmetries, which now will become the BMS4 group. So again, as a generalization of what we saw in 3 dimensions. Okay, so maybe we can go ahead with this. So to understand this, we want to again describe gravity, but now 4-dimensional gravity in the so-called Bondi gauge. So how the Bondi gauge was introduced in this series of papers, which I invite you to look at. So basically Bondi considers coordinates and family of metrics. So again, coordinates, suggestively, I call them UR and now 2 angular coordinates, XA. So we consider coordinates and metrics such that the hypersurfaces at U equals constant are null. So meaning that this normal, d mu of the U coordinate, satisfies this null condition. Now we can also demand, or at least Bondi demands, that the angular coordinates, XA, are constant along null rays. This is equivalent to this further condition. And there is also a condition on the determinant of the angular metric. Bondi demands that the determinant of the angular metric is related to the metric QAB on the unit sphere. So we can explicitly show that if we impose this condition, this implies that the metrics that we're going to look at take this general form of this line element ds squared. And you can see now, if we go back a few slides earlier, that this is really a generalization of the Bondi gauge, which we wrote in 3-dimensional gravity. So we have again these 3 functions, beta, v, and u, but now there are 2 free functions u, because this has the angular index capital A and here capital B. So now you see that this contains 6 free functions of the coordinates in this Bondi formalism. So for example, you can see that this family of metrics contains, of course, the familiar Schwarzschild metric. For the Schwarzschild metric, you just take beta to be 0, u to be 0, v is just minus r plus 2m, the Schwarzschild mass, and the metric on the 2-sphere here, HAB, you take this to be the unit metric on the 2-sphere, and this will give you the Schwarzschild metric. Now to go further in this Bondi formalism, we have to of course, allow for a more general family of solutions because we want more than just the Schwarzschild solution. So we have to start solving Einstein equations and see what type of fall-offs is imposed by the Einstein equations. So we saw in the case of three-dimensional gravity, or at least we didn't show this explicitly, but in fact, I hope we have time, but the idea was that at the end of the lecture, we do a very short session introducing some, I just want to give you a short mathematical notebook that actually computes the charges in three-dimensional gravity. And you could use this, sorry?
You have 15 minutes left.
Yes, yes. So I don't think we'll have time to do this, but I will give you the notebook and I invite you to play with it and to actually confirm all the calculations which we mentioned in the three-dimensional case. So in the three-dimensional case, what I wanted to say is that we were able to show that we have an explicit family of Schwarzschild metrics, and there was no expansion in this family of Schwarzschild metrics, no radial expansion, essentially because a three-dimensional gravity is topological. So because of this, the form of the metric which we had was exact. There was no radial expansion. Now in four-dimensional case, this is obviously not the case. The theory is not topological, so we cannot write an exact solution, but instead we can still go ahead and look at the Einstein equations with this ansatz for the Bondi form of the metric, which we gave on the previous slide, and see what type of behavior, what type of asymptotic behavior on the fields is imposed by the Einstein equations. Well, if we do this, we will find that, well, the fields which are in the metric basically have this, so the 6 fields in the metric, V, beta, UA, and HAB, the sphere metric have to have this behavior. So what is the meaning of this? So this, in particular, identifies 3 functions of retarded time u and the angular coordinate x. One of them we already had in 3D is the Bondi mass aspect. So again, the Bondi mass aspect, you can think of this as the angular density of energy measured at a point on scry, a point u, looking at the direction on the celestial sphere at the direction xa. So this is a quantity which we already had in 3 dimensions, right? We had this field m. Now in purple, we also have the angular momentum aspect. So again, we had this in our 3-dimensional solution space, but of course in our 3-dimensional solution space, because the angular metric was just, so the angular part was just 1-dimensional. It was not a celestial sphere, but a celestial circle. We only had one component of angular momentum aspect. So now in 4 dimensions, this is replaced by 2 components of angular momentum aspect, NA. So now this just for the moment generalizes what we had in 3 dimensions. But now the new thing, the new ingredient, which is of course specific to 4 dimensions and which we should see appear somewhere, we should see some difference between studying metrics in Bondi Gauge in 3 dimensions and metrics in Bondi Gauge in 4 dimensions, because 4 dimensions has gravitational waves, has local degrees of freedom. And because of this, we see that in this expansion, we have a quantity which appears, we call it usually CAB, and CAB is representing the radiative modes of the gravitational field. So more precisely, CAB is a symmetric traceless tensor, and typically what is an important physical quantity is the derivative of this tensor along the retarded time u. This defines the so-called News tensor, the Bondi News NAB. So not to be confused with the angular momentum aspect, it's the same letter, but the angular momentum has 1 index and the Bondi News has 2 indices. So now we can take this, this asymptotic behavior of the fields, V, beta, U, and H, plug this in the ansatz for the Bondi metric, which we had on the previous slide. I mean, we can already read it on these follows here, right? I just plug it explicitly in the metric to put this again in the form of a line element. And just to show explicitly that this takes the form of the Minkowski metric, this is in blue. And again, in the follow-ups above, you see that the minus R piece and the unit sphere metric QAB here, these are responsible for the Minkowski metric at leading order here. And then we have these terms, okay, which depend on these new quantities. So the mass, the angular momentum aspect, and the radiative modes, CAB, and then plus subleading terms. So now, just like in 3 dimensions, also, I really want to kind of contrast here what we saw in 3 dimensions. And again, I invite you to check everything we saw in the 3D case with the small Mathematica notebook. So just to contrast everything, we explained that in the 3-dimensional case, the family of Schwarzschild metrics that we had in Bondi Gauge solves all of the Einstein equations, provided we impose 2 evolution equations, 2 constraints. And in 3 dimensions, these constraints were relating the U derivatives of M and N, so of the Bondi mass aspect and of the angular momentum aspect. So here, of course, we have a generalization of these evolution constraints. They take, of course, a more complicated form. So the U derivative of M is given by this expression here, and the U derivative of N is a lengthy expression which I chose not to display here, but you can find this in many references. What I want to show you, for example, here, what we can already kind of learn from this construction is, you see there is a very important minus sign here in this U evolution equation for the Bondi mass aspect. You see that if we were to integrate this Bondi mass aspect, so as we said, this is the angular density of energy measured at the point U in the direction XA, in some direction on the celestial sphere. So if you want to integrate this quantity over all of the celestial sphere, so imagine that we compute the integral of du of m over all of this 2-dimensional celestial sphere, you see that this is a total derivative here. So sorry, these they are covariant derivatives with respect to the metric QAB. So this first term drops because it's a total angular derivative, and we are left with the second term, which is the squared of the news tensor. And again, the news is the time derivative of this radiative mode tensor. And importantly, there is a minus sign here. So this is telling us that when integrated on the sphere, this evolution equation for the Bondi mass aspect is minus n squared. So this is the so-called Bondi mass loss formula, because the squared of the news tensor is essentially a measure of how much energy is radiated away in the spacetime. So we see that this formula is telling us that this Bondi mass loss formula, which just follows from this evolution equation integrated on the 2 sphere, is telling us that the Bondi mass of the system is decreasing. So this is due to this minus sign, because the spacetime is emitting gravitational radiation as measured by this Bondi news NAB. So now, just like in the 3-dimensional case, we can look at the asymptotic symmetries here. So it's the exact same construction as in the 3-dimensional case, except that now, once again, we don't find exact asymptotic killing vectors, because now, again, this is we are in the physical 4-dimensional case. So we have to keep track of these subleading terms. And sorry, I forgot the plus sign here in the angular component. But again, we can construct the asymptotic killing vectors which preserve the family of metrics in Bondi Gauge. And okay, so if we did this, we would find these killing vectors. So again, with U component, radial component, and angular component psi A. Now, the important thing to mention here is that the function on the sphere, T, is completely free, while the 2 functions on the sphere YA, they have to satisfy the conformal killing equation, which is this equation given here. Now, if you compute the bracket, so we can compute with this modified bracket star the algebra of these vector fields. And essentially, again, we're trying to keep in mind what we did in 3D and try to understand the generalizations. T now are the 4-dimensional version analog of what we call the super translations in 3D. So these are the 4-dimensional super translations. But because this component Y on the 2 sphere has to satisfy the conformal killing equation, because of this, the part which is due to these rotations on the celestial sphere is only the Lorentz algebra. So unlike what happened in 3 dimensions, where all of the Lorentz algebra or all of the Lorentz group was enhanced to what we call the super rotations, so arbitrary angle-dependent Lorentz transformations in 4 dimensions. At least this historical version of the construction of the Bondi Gauge metrics and the Bondi Gauge asymptotic symmetries leads to this BMS4 algebra, and this is the algebra of Lorentz transformations in some direct product with the super translations. So again, which are arbitrary angle-dependent translations. So now, just to mention, you could ask yourself, why is it that in 4 dimensions we only find the Lorentz group here instead of something like the super Lorentz group, so the analog of the super rotations which we had in 3 dimensions, or even you could imagine having here all of the diffeomorphisms of the 2-sphere. Well, this is to be the answer is to be found in the precise form of the Bondi metrics which we have chosen. In fact, in this original construction of Bondi and his collaborators, there is some, of course, some further assumption and ansatz on the form of the metric that they consider. And this has to do in particular with the form of the metric, the angular part of the metric on the 2-sphere. And okay, I don't think we will have time to explain more the details, but maybe Laurent later on Friday, or maybe Andrew in the next talk will maybe mention this, but there are essentially ways to consider more general family of solutions, more general family of metrics in Bondi Gauge. So generalizations of the historical Bondi Gauge, which we presented here, in such a way that the group of asymptotic symmetries has also an enhancement of this Lorentz component, which is here. And this enhancement can be arbitrary angle-dependent Lorentz transformations, so super Lorentz, or even all the diffeomorphisms of the celestial 2-sphere. Okay, I just wanted to mention, I think I will skip this part on the super translations here. How much time do I have, Christophe?
10 minutes before the end of your time, but if there is any question, then it should be maybe better to ask now if there are any questions, and if there are not, you can continue.
Yeah, are there maybe questions I can?
Yes, there is one question in the chat. If you want to read it, in 4D asymptotic flat spacetime, the super translation charges at null infinity correspond to the Bondi form momentum, and the non-integrable part of the boundary charges can be interpreted as a gravitational radiation. If there are any analogs in 3D case.
Yes, thanks for mentioning this. So in fact, the last thing which I wanted to mention, so here just to mention very briefly what I wanted to conclude with in this section was to explain a bit physically, and I think this will be mentioned in the next talk, that these BMS symmetries in 4 dimensions, they are intimately related to something which is observable, so to a physical effect, which is called the displacement memory effect. And this is intimately related to the role of the super translations in 4 dimensions. So this is just what I wanted to discuss here. Before discussing, actually, what I did not discuss here so far, but what we discussed in 3D was the form of the charges, the charges associated to these BMS4 vector fields. So here I just wanted to emphasize the physics of these super translations in relation with the displacement memory effect. So maybe I skip this and I just go to the form of the asymptotic charges. So to answer the question and to compare with what we had in 3D. So now we also have all the ingredients to compute this, because we gave last week the explicit expression for the charges, delta bar, delta slash of the diffeomorphism generator D. So we gave the expression for this charge. The expression which we gave was actually valid in all dimensions, in 3D, in 4D. So in principle, you can apply it here, again, using this family of on-shell metrics and using these asymptotic killing vectors. If you use this to compute the charge associated with these asymptotic symmetries, well, you will find that the charge always has a piece which is not integrable. So you see that the first piece here, I wrote it as a total variation. This again looks a bit like what we had in 3D, because the super translation generator T is paired with the Bondi mass aspect M. The Lorentz generator on And the two sphere is paired with the Bondi angular momentum aspect, n. But now there is a non-integrable piece here. You see that there is a news tensor NAB times the variation of CAB. And because the variation is here in the middle, you cannot, well, this piece is obviously not integrable. So the interpretation of this is that in 4 dimensions, precisely because of the presence of this news tensor, which is the fact that this space-time can have gravitational radiation, well, the charges are neither integrable nor conserved. So I think you were, the question was asking if there is an analogous of this in 3 dimensions. Well, there is no analogous of the non-integrability, because as we showed, the charges are integrable in 3 dimensions. And they should be integrable in 3 dimensions, because in 3 dimensions, there is no gravitational radiation. So now we also did not explain really in details what is the relationship between the presence of radiation. There is a subtle interplay between the presence of local degrees of freedom, so the ability to have radiation, the conservation or non-conservation of the charges, and the integrability or non-integrability of the charges. These things are intimately related together. And of course, in 3D, we have no issue with integrability or conservation, as we showed, because there is no radiation. Here we see that explicitly in 4D, the obstruction to integrability comes from this piece, which is precisely related to the existence of news, namely gravitational radiation. So I hope this answers the question.
Thanks, Marc. Is there any question? You can raise your hand or just put it in the chat. And if not, then Marc, you can still have 5 minutes if you want to say something more.
Yeah, if not, maybe, so this was giving some bibliography, and I just wanted to, in fact, yeah, just motivate. The last thing I wanted to do, unfortunately, we won't have time, was to discuss a bit some numerical aspects. So the motivation was just to say that, of course, these calculations, which we did, for example, in the 3D case, they are doable by hand, but they can get extremely lengthy and a bit tedious. Especially it's if you want to find the asymptotic killing vectors, compute the charges, compute the algebra, it can be a bit complicated. So it's very convenient, on the one hand, to check your calculations, and on the other hand, that you, sometimes it's not just something which is in a paper which you want to check. Sometimes you want to actually discover things for yourself. You're looking for a family of metric. You're looking for vector fields. You're looking for the right form of the charges. And if you do this, of course, whenever you modify your ansatz for the metric, whenever you modify your ansatz for the vector field, you don't want to compute everything by hand every time. So of course, this is why it's useful to do it with a code. There are already very powerful codes which exist. So there is this Riemannian geometry and tensor calculus package in Mathematica. There's also a very powerful package by Geoffrey Compère, which computes the surface charges. So of course, you're free to use these packages, but I just wanted to kind of motivate the fact that it's also useful to have your own code that you wrote yourself, because then you can better understand what these codes are actually doing. There is no black box in the code. You can really understand what it's doing. So I also wanted to apologize because I wrote this with a commercial software, and it's a very short code, but it computes essentially, so it's a 3-dimensional code. It computes the Einstein field equations. Actually, this works, the Einstein field equation part works in any dimension, but then we apply it for metrics in Bondi Gauge in 3 dimensions. So then we check explicitly the killing equation with the killing vectors which we gave. We explicitly check the transformation of the fields M and N, and then we compute the asymptotic charges. So I invite you to just use this, and also if you want, translate it to any other language and generalize it to 4D and to anything you want. And I don't know, I have 3 minutes, maybe I can just, can I just?
If there is no question, you can, I guess. Still no one is raising its hand and nothing in the chat, so yeah.
Okay, so I will put the code on the Mathematica, on the, sorry, on the
screen.
Yes, and also on the page of the lectures. So Pietro, I think we can upload the code. So it's very short, and I just want to show you just the structure because it's, I mean, it's very simple. And I put just to show you that I wrote in comments everywhere what every step is doing. So it's just, we're basically defining a three-dimensional metric. This is the metric in Bondi Gauge, which we talk about. Then we're computing the Christoffel symbols, the Riemann tensor, the Ricci tensor, the Ricci scalar, and the Einstein field equations. And of course, if I launch this, I don't get 0 because as we mentioned, the fields M and N has to satisfy some constraints. And you see the constraint here is that the U derivative of N is related to the angular derivative of M. So now if I use these assumptions to enforce these constraints, we indeed get that the Einstein equations are satisfied. Here we were just checking, so this is the asymptotic killing vector which we gave for these metrics in Bondi Gauge. This is just computing the killing equation, so displayed here as a 3x3 matrix. Again, we mentioned that for these to be asymptotic killing vectors, the U and phi components, F and G, has to satisfy again a relationship. You see, relating the U derivative and the phi derivative. So to implement this, we just update the assumptions here. If I update the assumptions, okay, now we get this proper form of the action of a Lie derivative on the metric. From this, we can read the field variations here. And you see these field variations are exactly what we gave in the lecture. Here we can also compute, it's a short piece which computes the symplectic potential. This is, for example, the radial piece of the symplectic potential. And the final piece here computes the charges. And if we just launch this, we get, as expected, that the charge is F delta M plus G delta M. This piece here vanishes once we integrate by parts on the celestial circle, and we get the expected result for the charge. So this was just to illustrate that it's very quick to, once you have something like this, to compute the charges. So if this is a topic which interests you and you want to work on this, either for fun or for your thesis or anything, I invite you to try to write a piece of code which computes everything, because it will heavily simplify your life. Okay, and now I think we have to finish and to move on to the next talk. And hopefully, as I said, so the next talk by Andrew Strominger, there's also a talk by Nichols on Thursday and a talk by Laurent Friedel on Friday. I hope this will we'll be able to a bit better maybe understand what is going on thanks to the lectures which we've had. Okay, so thank you.